All right, question number 36. Here we go. So you want to write an equation of the line tangent. So we need three values. The x value is 1. The y value I would plug into here. 1 squared, take away 4 times 1 plus 3. 1 plus 3, that's 4. Take away 4, that's e to the 0. That would be 1. Double check and make sure I didn't make a silly mistake. And then the slope is the derivative of this. So the derivative of this is you copy it, and then the derivative of the exponent, 2x minus 4, and then you're going to plug 1 into that. So if I plug 1 into here, I know this, we just did that one, that's e to the 0, which is 1. Plug 1 into here, and I get negative 2 times 1, which is negative 2. So the equation then would be negative 2, x minus 1, plus 1. There it is. All right, number 37. Write an equation for line tangent. At x equals 1. So we know x equals 1. To find y, plug 1 in. 1 plus 2, 3. 3 to the 3, that's 27. And then the slope, we have to take the derivative and remember the derivative rule for that. So the derivative, I'll do that down here. Oops, I'll use the same notation. F prime at x. The derivative you copy. The derivative of x plus 2 is 1, so I don't need it. You can have it there. And then we need the ln of the base when the base is not e, right, like that. And then we're going to plug 1 into here. So if I plug 1 into here again, you get 27 times ln 3. I'm just going to use that. And then put it all together. The slope, 27 ln 3. And then x minus 1 plus 27. 38. Find the second derivative of this. In order to find the second derivative, we need to do the first derivative first. So this is the product rule. The first times the derivative of the second plus the second times the derivative of the first. So the first, the derivative you copy, and then the derivative plus the second, and then the derivative of the first is just 2. We need to do it again. Second derivative. This again is going to be the product rule, so that's the first. Actually here, this one I'm going to do to make life easier. They both have an e. Well, do I want to simplify it? I'm just looking to see if they simplified it. I'll make life easier. Or not? Whatever. Alright, I'll just do here. So product rule, the first times the derivative of the second. So I copy it, and then it has the hook, plus the second, negative 2, plus the second times the derivative of the first, plus the derivative of this, which is you copy it, and then the derivative of the exponent. There it is. It's not bad if you just follow the rules all the way in, and then when you're done, you're done. 39. In number 39, find the domain, x and y intercepts, extreme points, and points of inflection for the graph y equals x times e to the x, subtract e to the x. This is such an important question. So we're going to go one step at a time. And I really want you to think that how many steps can you do here before that? So when I think of the domain, is there any restrictions here that x can't be? And the answer is no. It's a continuous function. The next thing about intercepts, to find the x intercepts, we're going to make it equal to 0, and we're going to factor it. So you can see you can factor out e to the x from each one. E to the x will never be 0, so nothing comes from there. So the only x intercept's at positive 1, and it's going to cross. The y-intercept, we plug in 0 for x. So 0 times anything is 0. E to the 0 is 1, so when I put it together, that's negative 1. Next, I'm going to take the first derivative and see what do I remember what's going to come from that. So that's the first times the derivative of the second plus the second times the derivative of the first, and then negative e to the x, the derivative of that is just negative e to the x. Look at e to the x, subtract e to the x, and then all you're left with is, so these cross out, so you're left with x times e to the x. Make it equal to 0 and solve it. So the only value there that will work is 0. We'll give you the answer 0. So we're going to draw a number line, and we're going to do the first derivative test. Remember that? So I said it's good practice. Put in a negative number, a negative. E to the x will always be positive. So a negative times a positive, and then a positive times a positive at 0 is a minimum. So we just found a minimum. So when I plug in 0 here, 0 times anything, do we just find it? Oh, here. So when we plugged in 0, it's the y-intercept. So the y-intercept is a minimum. Concavity, we do the second derivative. So here again the product rule, the first times the derivative of the second, and the second times the derivative of the first, equal to 0. Factor out e to the x. And the only answer here is negative 1. So e to the x will always be positive. So negative 1 will give you the answer 0. Draw a number line again. We're looking for a concavity, and if negative 1 is a point of inflection. So for negative 1, go back here, and I would use this one right here. If you plug in negative 2, that's a negative times a positive. And if I plug in a number bigger than negative 1, it'll be a positive times a positive. So that's a point of inflection, and that also tells me concavity. So at negative 1, we have a point of inflection. So if I plug in negative 1, right? E to the negative 1, and negative e to the negative 1. I would say even to use your calculator. So, but e to the negative 1. I was just looking off the answer key. That when we simplify that, think of this as 2 points. So this is kind of close. It's close to negative 1, negative 1 ish. It's not. It's like a little less than that. We're going to put it all together. What are some points we have? We have x intercepts at 1, 0. That's it. We have a y-intercept at negative 1, which is also a minimum. And then at negative 1, and it's just like not quite negative 1, is the point of inflection. We know it's concave up right here. So it's not going to cross over, but it still decreases here. So there's an asymptote here. So it's concave down and then concave up. There are no x-intercepts. There's only one here. So it does decrease all the way through, but that creates an asymptote over here, and there's your picture. Man, that's worthwhile to do again, right? To go back and try it again from the beginning, to really try to understand how to graph that. Good question. Number 40. The second derivative is e to the x plus e to the negative x. The first derivative is 0, is 3. And then we have that point. So we're going to work backwards. We're going to integrate. So to find this, we're going to integrate e to the x and e to the negative x. Okay. So it might be easier just to separate this, and then we'll put it together at the end. So the antiderivative of e to the x is simple. Let's just copy it. Here, it's e to the negative x, but we have a hook. The derivative of negative x is negative 1, so we need a negative in front. So this is going to be this. Oops, with a little negative x right there. So, plus c. So the derivative of e to the x is there. The derivative of e to the negative x is e to the negative x times negative 1, which makes that positive, so they match. And then we plug in to find c. So we make it equal to 3. And plug in 0. And then see what c equals. So you can see that c is going to equal to 3. Make sure I'm doing it right. So the first derivative is e to the x subtract e to the negative x plus 3. Now we're going to integrate again. So the integration of e to the x is e to the x. The integration of e to the negative x is e to the negative x, but it has a hook of negative 1. So the negative and the negative is going to make that positive. And then the integration of just 3 is 3x and then plus c. Then we plug in the last point, which was 0 and 4. So make it equal to 4 and plug in 0. Be careful here. So because we're adding e to the 0 plus e to the 0, that's 2. 3 times 0 is 0. So if I solve this, c is equal to 2. So if I put it all together, it is e to the x plus e to the negative x plus 3x plus 2. All right, number 41. A good reminder to try things first. That when you play the video, don't play the whole solution. Do parts of it, chunk it, and see if you can do the next chunk. Find the area bounded. So as soon as I say that, in calculus, area is integration. I know I need to graph this. So 5 to the x is an exponential. This is what it looks like, just the graph of an exponential. Y equals 0. That's the axis. X equals 0, that's an axis, and x equals 1. So this is the area right here, and it says find the area bounded by that without using a calculator. So it's an integration question. It's going to go from 0 to 1. Top subtract bottom, which is 5 to the x, subtract 0. And then integrate it. So the integration of 5 to the x is 5 to the x, but it needs a ln x. Ln 5, ln of the base. So you copy it, but then it needs an extra part because the base is not e. And I'm integrating from 0 to 1. I first plug in 1. And then I plug in 0. So 5 to the 0 is 1, so it's just ln 5. And there's your exact answer. Oh, wait a second. What did I do wrong? Sorry. When you integrate, you don't times. When you integrate, you divide by ln 5. It's not the mistake part, right? It's like, oh, I made a mistake. How can I learn from it part, right? So I divide by ln 5 when you integrate. Now plug in 1. Now plug in 0. And you have your answer. All right, 42. Approximate an integration using a Riemann sum. Let's see if we remember how to do it. So in part A, it's a left Riemann sum with 4 equal subdivisions. So we're going to go top subtract bottom divided by 4. So the width is 1/2. I start with that. A left Riemann sum. Sometimes it's good to draw a number line, and we go from 0 to 2 and realize that every half creates the rectangle. So the first rectangle goes 0 to 1/2. So a left would mean I use 0, plug it in, and that height is 0. The next goes 1/2 to 1, so I'm going to use 1/2. I'm not simplifying it. The next one goes 1 to 3/2, so I'm going to plug in 1. And then the last one is 3/2 to 2. So I use 0, 1/2, 1, and then that. That's the 4 rectangles. Sorry, 3/2. And it's done. In part B, it says the trapezoidal rule to do the same thing. Again, 4 equal subdivisions, so we already did that part. Now the trapezoidal rule starts with 1/2, and then the width is 1/2. Again, I'm going to use this number line. So the first height, you plug in 0. The second height, you double it. The next height, you're going to double it. And I'm just using these values because I already did them. The next height, you're going to double it. And then the last height, which we didn't have to do for that, is plug it in 2. So it's 2e to the 2. And that the first and the last height is singular. And then here it's double. So that 2 is only because I plugged in 2 into here. All right, 40e. 3, we're almost there. Set up, but don't integrate from 43 to 46. So the solid is formed by revolving region R. So let's try this again. So y equals ln x minus 1, y equals 0, x equals 4. All right, I know, it's been a while. So a logarithm, this gives me the asymptote. So the h value here is positive 1. Oops. Positive 1. There it is. So there's positive 1. And I'm just going to draw the general shape of it, right? In terms of what's happening. And so we have y equals 0. We have x equals 4. And then we have our region right there. Now, what would make this equal to 0? So what would make this equal to 0? I'm going to write it exponentially to find it. So you take the function equal to 0 and solve it. So what's inside the logarithm? The base to the exponent 0. So add 1. So this right here, I needed that number. That's 2, and this is 4. So now I can, that was the hardest part. So then in 43, we're integrating from 2 to 4. And it says revolved around the x-axis. So it's bounded to the x, one circle. And it's top subtract bottom. So that's ln x minus 1, subtract 0, and then there's the setup. So I'm just going to keep going, referring back to this graph. So there's the answer for 43. Revolved around y equals negative 2. So y equals negative 2 is below it. So that's a washer. So first I set it up. That's 2 of them. And then we go top subtract bottom. So we have the logarithm, subtract bottom, which was negative 2. So when you subtract a negative, it's adding. And then the little radius is here. It goes 0 to negative 2. And again, when you subtract a negative, it's positive. Number 45. Now the solid's formed revolving around the y-axis. So if I revolve this around the y-axis, now I need to change this. So if I write this exponentially, so if I change this, because I need to know what x equals. what's inside the logarithm, the base, into the exponent y, and then I need to solve for y. Or what am I doing? Oh no, well why am I doing that, right? Why not use the shell method? I wasn't even thinking. So, because it's parallel to use the shell method, that way, because do you really want to solve for y? This becomes a pain. So instead of making it in terms of y, if we do the shell method, it's parallel, so it's still in terms of x. So the shell method starts with 2 pi, still 2 to 4. The radius for it is the y value, or the x value, I mean. So the radius is just, it's right subtract left. So that the x value subtracts 0, that's x. And then the height of it, in terms of what's happening, is still top subtract bottom. So that's ln x minus 1, subtract negative 2, or add 2. So that's top subtract bottom. Oh no, wait, sorry, because we're not using this line, so we're using this one, right? So it's just top subtract bottom, which is 0. We're using this right here. All right, one more. That was the new one. 46. Semicircle cross sections, perpendicular to the x. So a semicircle, we divide by 2. And then when I go top subtract bottom, which is ln x minus 1, I have to divide it by 2 for the radius. So ln x minus 1 is the diameter, divide by 2 for the radius, and there's your setup. Good question. 47. We're almost there. Find the average value. So to find the average value, it's an integration question. I'm going to integrate that. I'm going to make it calculus friendly right away. And then you divide by the difference of the bounds. So 3 take away 2, which is 1. To integrate this, the derivative of this is negative, so I need a negative in front. So it starts with a negative. And then I add 1 to the exponent and divide. And I'm integrating from 2 to 3. Dividing by 1 doesn't change that. And then I'm going to plug in top, subtract, plug in the bottom. And when you subtract a negative, you're adding. Oops, I got to plug in 2. So I plugged in 3, and then I plugged in 2. No. So I plug in 3, I plug in 2, and that's fine. If you wanted to simplify it, it's 7 over 24. I don't care. This is good right here. 48. A rectangle is inscribed under that curve, and there's a picture of it right in the book. And it says, find the point as shown in the figure that produces the rectangle having the most area. All right, optimization. That's a derivative question. So we need to have an equation for this rectangle. So the area of this rectangle we know is length times, start from here, is length times width. When I look at the length or the width or the base and the height, I'm using the y coordinate and 2 x's. In the question it says that y equals 4 over 1 plus x squared. So I'm going to multiply that together. And then this is a derivative question. So I'm going to take the derivative by doing the product rule, the quotient rule. Been a while. The bottom times the derivative of the top minus the top times the derivative of the bottom and the bottom squared, and then you make it equal to 0. Now, just the numerator I need. So if I just look at the numerator and make it equal to 0, that's what I'm going to do. So I'll combine like terms. And I think when I solve it, x is equal to 1. So what point gives me a maximum area? X is 1. If I plug 1 back into the function, that's the function right there for the y coordinate. If I plug 1 in here, 1 plus 1 is 2, 4 divided by 2. So that point, 1, 2, produces a maximum rectangle. Last one, number 49. Length of the curve. Y equals 3x squared plus 5x subtract 1 between the x intercepts. Alright, here we go. To find the x intercepts, we make it equal to 0. We factor it. I can't factor that. So, I got to use a calculator. The whole thing's a calculator question. So, I got to use a calculator to find the x intercepts. So, menu, algebra, solve, and I'm going to type that in. 3x squared plus 5x, take away 1, equal to 0, comma x. And the x intercepts are right there. So, I'm going to now integrate from those. Sometimes I'm like in a good highlighting mood. See if I can do that. Maybe I need to use 2 fingers here. There it is. Highlighting now. So highlight over it. Control C. And then come here. That's the lower bound. Control V. And I'm going to do the same thing. I hope I can do it. Click it, press down, and move to the right. There it is. Control C. Control V. Alright, so there's my lower and upper bound. Now the formula, which is the square root. 1 plus, parentheses, derivative in terms of x, and then I type in the equation, which is 3x squared plus 5x subtract 1. I have to square that. That's why I have that extra parentheses there. And then dx. I get 6.666. It's a lot of sixes. That's it. That's the answer. So let's write down. What would I write down here? So the intercepts were 0.180 and negative 1.847. The setup goes negative 1.847 to 0.810. And then it's the square root of 1 plus the derivative of that squared. Now the derivative of this is 6x plus 5. Why not, right? And then dx. And then when you integrate that, we get the answer to this. Happy. It's over. Mr. G Math over and out. Until next time.